So let's talk about supercomputers. Supercomputers do an awful lot for us every day, and we don't realize it. Supercomputers are the AI factories, but they do even more than that in terms of digital twins and other types of simulations. Why am I showing you pictures of rocks? Here's an example of what a supercomputer can do for you. In just a few weeks, as a collaboration between Bay Area companies and large labs, supercomputer found 30 times more minerals than had been discovered in all of human history, just by looking through and sorting solutions. So there's something supercomputer can do for you, right? But you might say, well, what does 30,000 new minerals do for me, right? I mean, how's that gonna impact my life? And so here's some way that it impacts your life. These are cancer cells. Supercomputers can do digital twins of your body, and they can tell you if you have cancer in a certain portion of your body. We can model literally every single red blood cell in your body, all the veins, all of the arteries. And we can do a simulation that will tell us if part of these cancer cells break off, where are they likely to land in the rest of your body. This tells us where to look for metastasization when we're looking into individualized healthcare. Right? They can do more than just cancer care as well, but individualized healthcare, all supercomputing. You're gonna have a supercomputer at your hospital in the future, sometime in the future. What's another thing that supercomputing can do for us? New materials, new technologies. So this one's from the Bay Area. This is a collaboration between Google and Lawrence Berkeley National Laboratory. In just a few weeks, they found hundreds of new materials for green applications. Either they're more efficient to use, they're lower CO2 emissions, they could be used for renewable energy. Lots of different materials in this space as well. So what are supercomputers doing for you today? All of this is what they're doing for you today. And some of it, like personalized medicine, they may do for you tomorrow. They also do all of our AI, right? So all AI is enabled by supercomputing technologies as well. This is not new. We've been doing this for ages, right? Some of the oldest computers at this location where we currently are were originally supercomputers, right? So everybody always wanted to get the most compute that they possibly could from a supercomputer. Just now we're in completely different orders of magnitude than we were in the past. So what is a supercomputer really made up of? I've used the word supercomputer, but I haven't really defined it for you yet, right? What's the basis? A supercomputer starts with a fairly regular commercial server. So regular commercial rack server, great, we have one of them, right? The real power of a supercomputer is unlocked by an area that we work on here at Queen's, which is networks. So the power is not in the individual computer. The power is in wiring together multiple different computers with very high-speed networks. Once we do that, computers can work collaboratively. Okay? So if we just put a whole bunch of computers in a data center, we can create a very large capacity. These are called capacity systems to be able to do things. Think about this as the Netflix or the YouTubes or the Google searches of the world, right? I have to do a whole bunch of tasks that are all distinct. Everybody here in the room or everybody out there on the web can all do a Google search right now, and they're all independent tasks. One person's Google search doesn't depend on another person's Google search, right? So I can build capacity without having to have these different computers talk to each other at all. Supercomputers really are the capability class systems. We refer to them as capability class systems because they give us new capabilities that other types of computers don't have. So what is AI? AI was a capability that we got from being able to make supercomputers large enough that they could crunch through enough compute to make them useful enough to be able to chat to you, right? So it's simply a compute capacity problem that we're trying to solve, right? We could think about this as an example from Livermore or Frontier. So Frontier is the #2 supercomputer in the world. It's out in Oak Ridge, Tennessee at Oak Ridge National Laboratory. And if you take your laptop and you work on a problem, what you can solve mathematically in your laptop in about 4 years, Frontier does in about 53 seconds. So that's a huge difference in capacity between these two systems, right? And how does it do it? It does it by talking to each other. Okay, so we'll talk a little bit about networks, but let's think about what this actually means. Here's an example. okay? I own a restaurant and I want to make burgers, right? Somebody comes to me and says, we need to figure out how to make 1,000 times more burgers. And I say, great. Get lots more people, right? Make a lot more burgers, and we'll have 100 restaurants, and we'll have 1,000 chefs, and we'll make 1,000 times more burgers, right? Great, hopefully we'll sell all of them, right? This is hard though. Okay, so I need to make a burger 1,000 times faster than we currently make them. I just need one, but I need it made 1,000 times faster than we can currently make it, right? You might say physically impossible in this analogy, probably true. But if we convert that over and we say instead, everybody in this room needs to calculate a sum of numbers. And I split them up and I give everybody 50 numbers. You sum up your individual numbers. But now we have to find the universal sum of that number here in the room. What's the key bottleneck that we'll have? How you communicate with each other to tell everybody else what your number was so that everybody gets the sum, right? Communication is the key in supercomputing. And what is communication? Communication is networks. So to put that in perspective, a network on a supercomputer is typically the only component that we purpose build in each generation. So companies sell specific purpose-made networks for supercomputing. You've seen bleed over in this recently. You know, NVIDIA sells InfiniBand, the Mellanox product line, to everybody now. That was originally a supercomputing product. I worked on it in the early 2000s when it was just a supercomputing exclusive product, right? But it's now bled into the mainstream. The key to these networks is the following. The networks as we have them for supercomputers rely on the fact that we can communicate quickly in terms of latency. What does latency really mean? Latency is the time it takes me to send my data to you, something info of value to you, and you receive it and acknowledge it, okay? So it's the difference between me sending a letter to you and me sending an instant message to you. Supercomputers are the instant message. We actually work about 1,000 times faster in terms of latency than a typical commercial network. Bandwidths are normally only 2x, about twice as high as a traditional network. But these network cards are expensive. What we've worked at Queen's, and I've worked at it for a long time, is building the interfaces that express how you use these networks through software to hardware. It's the key to how we get from point A to point B with regards to do that 1,000x better latency that we have. We cut out a lot of stuff in between, and we do a whole bunch of fancy stuff to be able to enable those things, but that's the way that we build very high-speed supercomputers and actually get them to work together. We're always building new networks. Now, what does this really mean, right? We talked about the 4 years versus 53 seconds to compute, but there's a lot of terminology behind these things. So during my introduction, you heard about exascale class supercomputers. What does that really mean? Supercomputers worldwide are ranked based on how fast they can do certain calculations, mathematical calculations. Dense linear algebra actually is the main one, even though people don't use it as much anymore. And what they're ranked on is how many floating point operations they can do every second. Basically, how many decimal numbers can you multiply together in a second, right? Your laptop working at gigahertz speeds can calculate billions of flops, floating point operations, per second, right? If you go home and you've got a PlayStation or the kids have an Xbox Series X, whatever it happens to be, that graphics unit will process teraflops, so thousands of billions of calculations per second. A reasonable supercomputer in this day and age will calculate petaflops. That's millions of billions of operations per second, right? And the best systems in the world, and only a few have achieved this, are actually at the exaflop era. That's a billion calculations per second. That can be hard to think of. We think, well, what are the practical ramifications of this? And if we take an example here from the Bay Area, we've been able to do in the past simulations about earthquakes. Okay, and we've been able to look at the entire Bay Area, been able to basically design out the buildings, shake them, and see what happened to the different buildings. And everybody said, oh my goodness, really tall buildings are in danger of earthquakes in the Bay Area, right? That's because in the past, with petaflop computers, we were able to model the ground as basically just ground, right? It was one solid object. Exascale let us model the ground as multiple different layers of what the ground actually is and all the interactions between those different layers of the ground. So now we can find out that in the Bay Area, medium-sized buildings, medium-story buildings are actually in more danger because of where they're located, and the ground underneath can liquefy. Why? Because now we can simulate all the different parts of the ground actually rubbing against each other and what actually happens in that physics. So supercomputers provide us a way of understanding our world and understanding it better as well. And in the future, yes, you're going to see AI models do a whole bunch of interesting stuff as well in helping us understand these things, but you can see a lot of traditional digital twins and simulations as well. Let's talk about AI for a second, or more than a second. So AI is basically a big, gigantic compute problem, right? So it's the equivalent of take everything that everybody ever wrote on the internet and shove it into a model, look at the data that's available for it, and crunch it. Basically, make some sort of coherence between it, right? It's a big, gigantic correlation machine, essentially. Oh, excuse me. I am greatly oversimplifying all of AI by saying it is a correlation machine, but just bear with me for a second when I say, essentially, it is trying to correlate and predict the probability of outputs based on inputs that we have. When you use this in a supercomputer, though, one of the biggest challenges to everything that we do in a supercomputer, because it's made up of many, many other computers, is how do you chop up your problem? How do you actually make the problem small enough that each computer has enough work to do, but then you can add that all together to make one big problem as a whole, right? The simplest way to think about this is traditional simulation. When we do simulation of your body or whatnot, I guess what we actually do, we actually chop it into really, really small cubes, and then we just use those really small cubes as a representation of the actual physical world. It works as long as you make the cubes small enough, okay? AI has the same problem. We have a gigantic amount of input data, and we need to create a very large model, and we need to be able to figure out how we chop these things up and make them work. So what do we do first? One of the methods is you chop up your data. So you chop up your data and give it into each individual computer or each individual GPU, and you go from there. That's data parallelism. You can also do model parallelism, where you share the data, but then you chop up different portions of the model, and you recombine them later into the one larger model. How you chop that up is the difference between what some people call model parallelism and other people call tensor parallelism, but basically it's essentially the same task. We take a really big problem, we chop it up, we assign it out to different portions of the supercomputer. They all have to talk to each other because they're collaboratively working on one big problem, and then we eventually recombine everything back together to get the end solution that we want. So AI is essentially a supercomputing problem as well. The difference is that now everybody wants to spend billions of dollars in supercomputing, where 20 years ago, mostly governments wanted to spend money on supercomputing. Why did governments want to spend money on supercomputing? Let's talk about the global landscape of supercomputing for a second. The Japanese, for instance, are big into supercomputing. What do? Things that you would expect the Japanese to do: earthquake modeling and tsunami prediction, things that really matter to them, right? That's not something that a private business is going to do, but it's something that a government would like to do. The US uses it for plenty of different things: fundamental scientific research, national security, defense, all sorts of things get used for supercomputers in that space. And the US typically leads the world in terms of total supercomputing power. Right now they have more than 4 exaflops of total power deployed in this in the country. We have Europe that heavily uses supercomputing as well. Europe has some useful, interesting use cases. They use it not just for research, but for example, Italy's biggest supercomputing user is their power utility. Why? It's really useful for them to make a whole bunch of money off of it because they maximize their grid through supercomputers. They've been doing that for a really, really long time, right? The French use it for a variety of different tasks, so do the UK, very large supercomputers over in Europe as well. So where does Canada stand in all of this? So before I tell you where Canada is, let me say part of my role at Queen's is fixing this problem. So our top supercomputer in Canada lies at, I think, 154 on the list as we count it right now. We're behind Poland, we're behind Brazil. We're like competitive with Czechoslovakia in terms of our overall compute. But of course, Poland and Czechoslovakia aren't entirely fair because they have access to all the EU supercomputers. They actually have way more compute than we do. Now, the government has recently announced $2 billion to spend on AI infrastructure and compute. A lot of that is going to public research infrastructure as well as innovation supercomputing. We at Queen's have been very hard at work trying to build next generation large-scale AI systems. It's not going to be a $100 billion investment or 100 billion euro investment like the EU, but you'd be amazed at what you can do with small amounts of money when you're not the first to arrive at a brand new technology. And so what we're trying to do is build a top 20 supercomputer. 20 is pretty good, right? In Canada, on Queen's campus, for both industrial innovation with our industrial partners, as well as research, and enable AI education on campus as well. So we want to be one of the first universities that brings in real large-scale AI to teach it in classrooms and have students understand what they need to do to build out large AI infrastructure. So we want to teach people how to build these systems, because not a lot of people are out there training people on how to build these systems. They're out there building very large systems. I recently returned to Canada specifically to do this because I used to work on very large systems. And now I want to educate the next generation in these systems as well. So with that, I will leave you with the last Easter egg, which you've probably noticed. There are inconsistencies in some of these pictures. This presentation is entirely AI done. I did that not because I'm lazy, but because I wanted to demonstrate to all of you that it's pretty good if you don't look very closely at where we are today. This is an actual application of supercomputing itself is this presentation, aside from what I said. So with that, thank you.